Welcome to our course on understanding how machine learning systems operate. In this video, we will break down the complex process into 8 simple steps. Let's get started. Welcome to the world of machine learning. At its heart, machine learning is simply about extracting knowledge from data. We can also call this process predictive analytics, or statistical learning. The goal is to build a system that can learn without needing direct, upfront programming. Instead of telling the computer exactly what to do, we give it data, and the machine figures out the patterns needed to make decisions. It is important to know that a working ML system is complex. The actual learning algorithm is just one small piece. A full ML system also includes business goals, the data infrastructure, how we watch the model's performance, and the underlying computer systems that make it run. This holistic view is necessary for success. What have we learned? The important point is that ML systems are much more than just algorithms. They are intricate systems driven by data and business needs. This diagram illustrates the key components that make up a real-world machine learning system. It starts with A, the business requirements, which define the goal of the system. This leads to B, the data stack, where data is collected and processed. The data then feeds into C, the ML algorithm, which is the core learning engine. Finally, D, the system monitoring and infrastructure. Make sure the model is running correctly and efficiently. Notice the loop. The performance results from D feed back into A and B, making this an ongoing iterative process. We must consider all these elements, not just the algorithm, when building a successful machine learning solution. This comprehensive approach ensures that the model not only performs well scientifically, but also meets real-world application needs. What have we learned? The key takeaway is that the components of an ML system are interconnected, emphasizing that a strong ML application needs support from robust data and infrastructure. Building on our previous overview, let us examine the fundamental distinction between machine learning and traditional software. In traditional programming, programmers meticulously craft the rules, or if-else decisions, by hand. We provide the system with inputs, along with the hand-specified rules, patterns, and the system reliably calculates the outputs. While efficient for straightforward tasks, this approach fails when the necessary patterns are too intricate for a human expert to define manually, such as recognizing a face in a picture. Machine learning flips this paradigm. We supply the system with the input data and the correct, desired output. The ML system then works backward to automatically discover the complex patterns, rules, required to map that input to the correct output. What have we learned? The important point is that ML excels at automating complex decision-making by learning the rules from examples, rather than relying on human experts to write them. This diagram clearly shows the difference in how outcomes are generated. On the top, for traditional software, you must provide the inputs, I1, and the patterns or rules, P1, that the programmer explicitly wrote. The software, TS, then calculates the outputs, O1. On the bottom, for machine learning, you provide the inputs, I2, and the desired outputs, O2. The machine learning process, ML, then discovers the complex patterns or rules, P2, itself. This learned pattern is the core of the ML model. The ability of ML to learn patterns from paired inputs and outputs, instead of being programmed with fixed rules, is why it is effective for sophisticated tasks like object detection and speech recognition. What have we learned? The key takeaway is the conceptual shift from explicitly defining rules to enabling the system to discover rules autonomously from data. Following the understanding that ML learns from data, we must now prepare that data properly. ML works best when the data is presented as structured data, which is organized and labeled in rows and columns, similar to a digital spreadsheet. In this format, each horizontal row is known as a sample or a data point. This is the fundamental entity about which the prediction will be made. For example, when analyzing housing prices, one house is one sample. The vertical columns are the features. These features are the descriptive properties of the samples, such as the house's square footage, its number of bedrooms, or its location. A crucial point to remember is that the resulting machine learning model will only be able to make predictions based on the information contained in the features provided. What have we learned? The important point is that the data must be organized into rows, samples, and columns features before any learning algorithm can begin processing it. This diagram uses a programming metaphor to illustrate how data is structured. The sequence of commits on the master branch represents the individual samples or data points, the rows of your dataset. The side branch labeled features represents the descriptive properties, the columns, such as feature A, B, and C. When these paths merge, they form the complete ML dataset structure required by machine learning algorithms. This structure is necessary because it tells the computer what entities exist and what properties, features, describe them, ensuring the model has the information needed for training. If any important descriptive property is missing from the features branch, the final model will lack that information, impacting its predictive power. What have we learned? We saw how samples and features combine to form the data structure, confirming that both sufficient quantity, samples, and quality, features, are required for robust ML systems. Building on our structured data foundation, we now explore supervised learning, the most frequently deployed ML method. This process is called supervised because it is guided by a teacher who provides the correct answers. We input labeled data, where the inputs, the samples and features, called the independent variable x, are paired with the known, desired output, the answer, called the dependent variable y. The algorithm's job is to analyze these numerous x, y pairs and extract the relationship, forming a reliable prediction model. For instance, given millions of emails labeled spam or not spam, the model learns the distinguishing characteristics. Once the learning process is complete, the resulting model can autonomously predict the output y for any new input x. What have we learned? The important point is that supervised learning requires accurate, predefined output labels to successfully learn the functional relationship between the input and output. This sequence diagram illustrates the step-by-step supervised learning process. Step 1. We feed the labeled data, x, y, where we know the answers, into the supervised algorithm. Step 2. The algorithm processes this data to learn the underlying relationships/patterns. Step 3. This results in the trained ML model, which embodies the learned knowledge. Step 4. When a prediction system receives a new, unclassified input, x_new, it requests a prediction from the model. Step 5. The model uses its learned patterns to produce the prediction, y_new. This clear flow highlights that the core of supervised learning is building a reusable predictive function from examples with known outcomes. What have we learned? We confirmed the training sequence. Data flows from labeled examples through the algorithm to learn patterns, resulting in a model capable of generating predictions for unseen inputs. Following supervised learning, we now look at unsupervised learning. This method is necessary when we have data where only the input x is known, and we lack any predefined labels or answers, y. Because there is no external teacher to check against, these methods are often considered harder to understand and evaluate. The algorithm's objective shifts from prediction to pure structure discovery, finding hidden groups, relationships, or ways to summarize the data. A primary application is clustering. Here, the algorithm groups similar samples together automatically, such as classifying topics in a massive text corpus when you didn't define the topics beforehand. Another useful technique is dimensionality reduction, which helps simplify data by reducing the number of features while retaining important information. What have we learned? The important point is that unsupervised learning is used to uncover intrinsic organization within data when labeling is unavailable, focusing on structure rather than prediction. This mind map highlights the purpose and nature of unsupervised learning. The central aim is structure discovery, intended to extract intrinsic knowledge and find hidden patterns because there are no labels available. To achieve this, we rely on core techniques like clustering, such as k-means, which groups similar data points, and dimensionality reduction, such as PCA, which simplifies the data's complexity. Since the input consists only of samples x with no target outputs y, the model defines its own categories, making it a powerful tool for exploratory data analysis. This is distinct from supervised learning, where the goal is to predict known outcomes based on historical examples. What have we learned? We established that unsupervised methods focus solely on the internal organization of unlabeled input data, using techniques like clustering and dimensionality reduction. After training, we must assess the model's quality, focusing on its ability to generalize, that is, its capacity to make accurate predictions on data it has never processed. It is vital that we do not test the model using the training data. Doing so would allow the model to score highly, just by remembering the inputs, masking its actual performance on real-world data. Therefore, we divide the initial dataset. A large portion, typically 70% or more, is dedicated to training the model. The smaller portion, the test data, is kept entirely separate and reserved for the final, honest evaluation. If a model achieves perfect accuracy on the training data, but fails miserably on the test data, it is overfitting. It learned the noise instead of the core patterns. Conversely, underfitting means the model is too simplistic to capture any useful patterns. What have we learned? The important point is that separating training and test data is mandatory to gain confidence that the model will generalize well in practice. This diagram illustrates the necessary flow for robust model evaluation. The initial dataset D is divided into training data T1 and test data T2 at the data split S phase. T1 is used for ML model training M. M is then tested against T2 in the evaluation step E. The outcome determines if we achieve generalization, P1, meaning high accuracy on T2, or suffer from overfitting, P2, indicated by poor accuracy on T2 despite potentially high accuracy on T1. This process ensures the model's predictions are trustworthy on future unseen inputs. We must always strive for generalization by validating performance on truly unseen data. What have we learned? The process shows how data splitting helps prevent misleading accuracy reports and identifies if the model suffers from overfitting or underfitting, which are major threats to generalization. With the model trained and thoroughly validated for generalization, we proceed to deployment. Deployment means integrating the model into a working environment where users or other systems can access its decisions. The act of generating outputs for new input data is called inference or prediction. We must choose the right prediction service based on speed requirements. Batch prediction is used for tasks that tolerate delay, processing large data volumes simultaneously, e.g., calculating all user credit scores overnight. Online prediction, conversely, is required for real-time applications, like search recommendations, demanding predictions for individual requests with minimal delay or low latency. A serious operational risk is that ML systems can fail silently. The model might be running smoothly, but if the predictions are unexpectedly inaccurate, users may not even realize the system is faulty, necessitating robust monitoring. What have we learned? The important point is that deployment requires choosing between batch and online prediction based on latency needs, and must include monitoring due to the risk of silent failures. This diagram illustrates the two main prediction modes once the model is deployed. Batch prediction handles a large historical data input, D1, at scheduled times, running it through the model, P1, and storing the aggregated predictions in bulk results storage, R1, for subsequent use, U1. This mode is high throughput but slower. Online prediction, shown below, handles a single input query, D2, in real time, delivering an immediate result, R2, directly back to the user, U2. This requires a low latency environment. Both utilize the ML model, but the infrastructure supporting the online system must be optimized for speed to prevent user frustration. What have we learned? We distinguish batch prediction for bulk, time-insensitive tasks from online prediction for real-time, low-latency applications. In summary, the entire machine learning journey is not a one-and-done setup, but rather a continuous iterative process. We structure this continuous effort into a predictable life cycle. The cycle starts with project scoping, where we precisely define the business goals and system requirements. We then move diligently through data engineering, cleaning and preparing our data, followed by rigorous model development and testing. Once deployed, the critical phase of monitoring and continual learning begins, watching the model for performance degradation or data distribution shifts. Finally, business analysis evaluates the model's real-world impact and feeds crucial insights back into the initial scoping stage, ensuring the system remains effective. This cyclical nature is non-negotiable because data in the real world is constantly shifting, demanding that models be adaptable and routinely updated to prevent performance decay. What have we learned? The important point is that successful ML systems are sustained through an iterative feedback loop that ensures the model remains accurate and aligned with evolving data and business needs. This flowchart shows the complete iterative lifecycle for an ML system, often called MLOPs. It begins by defining goals at 1, project scoping. The flow then proceeds through 2, preparing the data, and 3, building the model development. After 4, deployment, the most continuous phase is 5, monitoring and continual learning. This step is vital for catching the unavoidable performance drops that occur as real-world data distributions change. Step 6, business analysis, provides performance insights that directly influence the next round of scoping. 1. Guaranteeing that the model continually adapts and performs as intended. This ongoing feedback mechanism is the foundation for maintainable and scalable machine learning solutions. What have we learned? We finalized our understanding by seeing that ML systems require continuous operation and refinement through a 6-step iterative cycle to address shifting data and ensure long-term viability.